are sequential games of perfect information. So there are, thousands of games I want to think of. So let me just tell you what this means. I don't know write the formal definition. But a sequential game means that people move in steps. So first I move, then you move, then I move, and so on. So moves are in sequence. And I can observe the entire history of the game before I move. Is that okay? So there's nothing hidden. Is that clear? I can see your move, then you can see my move, then I can see your move, and so on. And eventually the game goes on. So it's also a finite sequential game. The game goes on, does not go on forever. So for example, the game of tic-tac-toe is a sequential game of perfect information, right? So I move, then you move, and so on and so on. Yes. The game of NIM. The game of NIM. It's a very simple game. It's a good bar game to play. So let's say these are matchsticks. So there's 2 matchsticks here, 4 matchsticks here, 6 matchsticks here. And the rule is that you can pick up as many matchsticks as you want, but only from one of these blocks. So for example, you go first, so you can only pick up one from here, or both from here, or one from here, or 2 from here, whatever. You cannot pick up one from here, one from here. That's not allowed. Is that okay? So you can pick up as many matchsticks as you want, but only from one block. Then I go, and I do the same thing. Then you go, and then I go, and so on. Whoever picks up the last matchstick wins. That's the game of NIM. Is that clear? Okay. The game of anti-NIM, on the other hand, is the same game, but whoever has to pick up the last matchstick would lose. Is that okay? The game of anti-tic-tac-toe, for example, is whoever has their X's and O's in a sequence loses. There are anti-tic-tac-toe competitions. The game of anti-chess is whoever gets checkmated first wins. Yes? So there are different versions. So every game has its anti-version. So this is the anti-NIM. So let's quickly play anyway, a quick round of anti-NIM. Anybody? So yes, you want to go first? I go first.
Okay.
Who goes first? I.
Go ahead.
I.
So like you can pick up more than one?
Yeah, remember, whoever picks up the last one loses. Yes, that's it.
Alright, I'll pick up the 4 in the middle.
The 4 in the middle? I pick up these 3.
Dude, you already lost.
Oh!
Alright, one more time. Who goes? You go first, I go.
I'll go.
Yep.
I'll just take one at a time.
I take one.
Okay, I'll take that one.
This one?
Yeah.
I take this one.
Play this game a lot. I'll take 1 out of the 4.
1? I take 1.
I'll take 2 from the 4.
2. I take all 3, yes. Anyway, so this is what the game of anti-NIM is. Is that okay? So let me give you one more example. I will tell you how to solve this game in 1 second. So it's a good way to make money off your friends also. So let's look at the other example is, so let me give you one more example. The example of pirates. I don't know whether you thought of this pirate. So think about, let's say there are 5 pirates, and there are 50 gold coins. Yes. So they want to negotiate how to divide these 50 gold coins among these 5 pirates. And here's how the negotiation is going to work. The oldest pirate, let's say I'm the oldest pirate, I start the negotiation and I say, okay, I'm going to keep this, you have this, you have this, you have this. I select the distribution. Is that okay? And then it goes to a vote. If half of us agree to my suggestion, then we split the coins in that order and we all go home. If more than half disagree, then I'm thrown off the boat and the second oldest pirate takes over. Is that okay? Is a game change? So I suggest a split, goes to a vote, democracy. Half votes for me, then we split the coins in the way I suggested. If more than half says no, then I get kicked out. Let's say the kicked out payoff is 0 or something. And then the second oldest pirate gets in, and now I get no shot at any of these gold coins. Is that okay? And then the second oldest pirate, again the same thing. He proposes something. If he gets kicked out, then the third oldest pirate gets over. So the question is, suppose there are 50 gold coins, and you have 5 pirates. and you are the oldest pirate, what would you suggest? Yes? 48? Yeah, hang on. He's already took my punchline away, but we'll talk about why it's 48 in 1 second. Is that clear? So that we'll talk about that. So let's go back. So how do we solve this sequential game in general? Right. The English auction, for example, is a sequential game, right? The poker is not quite perfect information, it's also sequential. So the way we solve it is very simple, is what we call backward induction. So let's take the game of NIM, for example, the game that we just played. How are we going to win this game? So I have to go and think about what is happening at the end of the game. That's my objective, right? If I know what to do at the end, then I know what to do at the previous step. And so I'll tell you what I mean by this. So when I was playing the game with him, I was trying to think of these following scenarios. Let's say we are in a situation where it's 2-2. There are 2 matchsticks left in both blocks. And it's your turn to move. Can you ever win from this position? So if you pick up 1, then I'll pick up these 2. Then you'll be stuck. If you pick up both of these, then I'll pick up 1 and you'll be stuck, right? So from 2-2, you can never win. Is that clear? How about from 1-1-1? You can never win, right? Because you're 1-1-1, I have to pick up this one. So 1-1-1, it's your move, right? You have to pick up this one, then I will pick up this one. You'll be stuck with this one, right? So from 1-1-1, you can never win. Is that clear? From 3-3, you can never win. Why? So let's say you pick up 1. So what is now? It's 2-3, right? What should I do? I should pick up 1 and make it 2-2. I know from 2-2 you can never win. Is the idea clear? So if there's 3-3, I just pick up 1 and I just pick up the other. If you pick up 1, then I pick up this one and make it here, right? And you lose from here. If you pick up 2, what should I do? I should all pick up all 3 and you'll be stuck with this one. If you pick up all 3, I should pick up 2 and you'll be stuck with this one. Is that okay? So from 3-3 you can never win. Are you guys all with me here? From 4-4 you can never win. Why? Because if you pick up 1, what is this? 4-3. What should I do? I should pick up 1 to make it 3-3. I know you all don't do it from 3-3. Is that clear? From 1, 2, 3, you can never win. Why? If you pick up this one, what is this? 2-3. Tell me what your move should be. Let's pick up 1 and make it 2-2. Is that okay? If you pick up this one, so 1, 1, what should I do? I should pick up these 2 to get 1, 1, 1. Is that okay? So what am I doing? So I'm going to the last step and then thinking of what to do in the step before, then thinking of what to do in the step before, and so on. And that's what's called solving by backward induction. Is that clear? So if I give you any game, so any game can be drawn like this. So I can say, let's say player 1 moves, and player 1 has 2 strategies, A and B. And then player 2 has 2 strategies, C and D. Then player 2 has 2 strategies, E and F. And let's say the game ends here, 0-1, 1-3, 2-2, and 1-4. What does this mean? That means if the game ends here, player 1 gets 0, player 2 gets 1, and so on. So can we solve this game? How would this game be played? The way to do that is we go to the last step. Look at this step. Player 2 is moving, right? What should player 2 do? Should he go C or D? If he goes C, he gets 1. If he goes D, he gets 3. So he should go D, right? What should player 2 do here? If he goes E, he gets 2. If he goes F, he gets 4. So he should go this way. Let me just make this 0.5. Is that okay? So you know what player 2 is going to do here, right? Then given that, you know what you have to do here. Why? Because if you go this way, you know that player 2 is going to go this way, and you get 0.5. Is that clear? If you go this way, you know that player 2 is going to go this way, and you'll get 1. Are you guys, is that clear? So you'll go this way. Is that okay? Yes? So all we have to do is go to the last step of the game, right? And see what the players are doing at these steps. Then we have to go to the step before and see what the players are going to do at that step. And then we have to go to the step before and so on. So that method is the backward induction. Is that okay? Yes? So what about the pirate problem, the one that he just talked about? So think about the last step of the pirate problem. What is the last step? Last step is everybody has been thrown off the boat, only 2 people left. So there are only 2 people left, and suppose you are the older of the 2 people. What should you suggest as a split? Yes? 50 nothing. That's simply a good split. So I said, I'm going to give 50, I'll give you nothing. Let's vote. Yes? So of course, you will vote no, I'll vote yes. But remember, all I need is half the votes. Half the surviving votes. Is that okay? So the last, if I'm so with 2 people, this will be the outcome. There's nothing you can do about it if you're the youngest pirate. Yes? So now suppose there are 3 people. What should we do? Suppose there are now 3 guys. And I'm the oldest guy. What should I propose? I know that if my proposal gets rejected, this would be the outcome, right? So I give this guy 1. I give this guy nothing, and I keep 49 for myself. So what am I suggesting? I'm suggesting, so there are 3 of us left. I'm picking up the youngest guy. I'm saying, you get 1, I get 49. Give the middle guy nothing. Let's go for a vote. So I, of course, vote yes, right? You, the middle guy, of course, is going to vote no because he's got nothing. Think of this guy. This guy is the guy, right? If he votes yes, he gets 1, right? If he votes no, what happens? I get kicked out. We go here, and he gets 0. So he'll agree to what I'm suggesting. Is that okay? So if there are 3 people left, it will be 49-0-1. That will be the choice. Is that clear, guys? If there are 4 people left, what should I do? I should give this guy nothing, give this guy 1, give this guy nothing, and keep 49 for myself. Yes? Is that okay? Why? Again, so these 2 guys, forget about these 2 guys, they're going to vote no. This guy is the important guy. Whether he's going to vote yes or no. Yes? If he votes no, remember that the game goes here and he gets 0 here. Why does he not get 0 here? Because the game goes here, this guy gets 0. Do you guys see what I'm saying? Yes. So this is the way you can fold the game back, right? And as he said, with 5 people, you're going to get 48 for yourself and give 1 to the other people. Yes. So that is what sequential games are. And this, of course, was discovered. This idea was by this guy Zeletin. So he and Nash, the Russell Crowe guy, they won the Nobel Prize in the same year. Apparently, this might not be true, so don't quote me outside this class, but apparently Nash tried to kill Zeletin in his undergraduate days. They were roommates. And Nash actually put some sort of electric bulb in his bag, or something that's really dramatic. They thought Zeletin was a Russian spy. Anyway, so that was. Anyway, so this was Zeletin. And so there's this famous theorem called Zarmella's theorem, which says that every sequential game can be solved this way. And you can see why, right? You go to the end and then you fold the game back. That's the idea. So, for example, the game of chess is solvable, right? The problem of solving a game of chess, of course. So there is an optimum way to play chess. Is it by Zarmella's theorem? Is that okay? All we have to do is draw this gigantic game tree, right, with millions and millions of arms, right, and go to the last step and solve all these last steps out. Is that okay? But theoretically, it is possible to do it. Yes. Just think of how complicated the game tree gets. If you think about the tic-tac-toe game, if I want to draw the tree of the tic-tac-toe game, how would that happen? So here's the tic-tac-toe game, right? No, that's too many. So if you're starting the game, you have 9 possible moves, right? You have 9 possible strategies. Is that okay? And from each of these 9 strategies, the second guy has 8 possible strategies, right? And so on. So the game tree looks really complicated even for a tic-tac-toe. Just imagine what it's going to look like for chess. Is that okay? But it could be solved. That's the idea, that you can actually solve this game using it. Okay. So now let's think about, but as you saw, the problem that von Neumann faced is to thinking about what I should do depends on what he thinks I should do and so on. That is absent for sequential games, right? We just go to the last step and we know what people are going to do in the last step. They're going to choose the one that's better for them, right? And then we can